Welcome to MAT 248 class, real analysis. Today I'm going to be talking on the principle of mathematical induction. Principle of mathematical induction, otherwise known as PMI. Now, PMI is a theorem that is used to prove mathematical statements that depend on the set of natural numbers n. So I'm going to write the statement of the theorem. Theorem PMI. It says let P of n be a proposition that depends on n natural numbers. 1. If P of 1 is true. 2. And then P of n plus 1 is true whenever P of n is true. Then P of n is true for all n in the set of natural numbers. This is the statement of the principle of mathematical induction. Now, in order to use this principle or this theorem to prove a mathematical statement, we need to go through 3 steps. Step 1 is to apply PMI. Follow these steps. Step 1. Show that Pn is true for n equal to 1. That's the first step. You show that Pn is true for n equal to 1. Then step 2. Assume Pn is true for n equal to k. You assume that Pn is true when n is equal to k. And then step 3, you prove now that Pn is true for n equal to k plus 1. Okay, so when we follow these 3 steps, we'll be able to follow these 3 steps to prove that a mathematical statement is true whenever we are given, using PMI to prove. Now let's take some examples. Example 1. Prove that summation I equal to 1 to n of I is equal to 1 over 2 n in bracket n plus 1. Now this is a mathematical statement that is always true. This statement says that the sum of natural numbers up to n is equal to half n into n plus 1. The left-hand side is addition of natural numbers up to n, while the right-hand side is just a formula that will give you the sum directly. Now we are going to prove this mathematical statement using PMI. So proof. We follow the step like I said before. So we'll take step 1. Step 1 is to show that the statement is true when n is equal to 1. Let me say that if step 1 fails, there is no need to go further. Since if step 1 fails, there's no need to go further to make the proof. It means the theorem is not, the statement is not true. So you just stop there. So let's check that it is true when n equals to 1. So we say for n equal to 1, our left hand side, which is summation I equal to 1, n is 1 now, will be of I, will just be put n equals to 1. The right will be equal to half 1 plus 1 is equal to 2, which is just 1. So we see left hand is equal to right hand side. Therefore, Pn is true for n equal to 1. Okay, now I come to step 2 now. Step 2. Step 2 is an assumption. Suppose Pn is true for n equal to k. So I'm going to write the statement, the truth statement when n equals to k. So the truth statement will be what? Summation I equal to 1 to k, replace n by k, of I is equal to 1 over 2 k in bracket k plus 1. That's the truth statement. So we'll just stop there. That's step 2. Now let's come to step 3. Step 3. Now let n be equal to k plus 1. We'll put n to be k plus 1. Now we're going to do from left hand side to arrive at a formula in the right hand side. So we'll say summation I equal to 1 to k plus 1 of I is equal to, we expand this. We know that this can be written as 1 plus 2 plus 3 plus up to plus k plus 1, which is simply equal to 1 plus 2 plus 3 plus up to k, then plus k plus 1, which is equal to summation I equal to 1 to k of I plus k plus 1. But in step 2, we have already assumed that summation I1 to k is equals to half k plus 1. So this is now equal to half in bracket k into k plus 1 plus k plus 1. I'll put in bracket by step 2. Okay, by step 2 we can do that. So this is now equal to k plus 1 is common everywhere. I bring it out, and then I'm left with half k plus 1, which when you simplify further, you will get half k plus 1 in bracket k plus 2, and that is proof. So we have arrived at that formula. So therefore Pn is true for all n set of natural numbers. So it's always true for that. Now observe that this is now our right hand side, the new right hand side. You see, if we go back to the original problem given to us, summation I1 to k equals to this. If I replace n by k plus 1, okay, then this should replace by k plus 1 plus 1 plus 1, which is k plus 2. So without just mere substituting, we'll work from the left hand side to arrive at what it should be in the right hand side. And so we got that answer. That shows the statement is correct. I take example 2 now. Example 2. Example 2, prove that prove that 11 raised to power n minus 8 raised to power n is a multiple of 3 for all n set of natural numbers. Okay, so this statement says that this expression here, 11 raised to power n minus 8 raised to power n, is always a multiple of 3 whenever you choose n to be a natural number, n from 1, either 1 or 2 or 3 or 4 or 100 or whatever. This thing will always be a multiple of 3. So it's a mathematical statement that is always true, but we are going to prove that it's true using principle of mathematical induction. So proof. Again, using PMI, we follow our 3 steps. Step 1, we show whether it's true for n equal to 1. For n equal to 1, okay, let us say our Pn is this statement given. So when n is 1, so that is P1 will be 11 to power 1 minus 8 to power 1, which is just 11 minus 8, which is what? 3. 3 in bracket 1. So that shows that it's a multiple of 3. That means 3 can divide the result completely without any remainder. Okay, now we'll go to step 2. Sorry, step 1. Step 2. In step 2, we assume, suppose Pn is true for n equal to k. So I'm going to write the statement, the truth statement when n is equal to k. So that will mean that 11 raised to power k minus 8 to power k is equals to 3. I can use a. A is just any real number. A is just any number, any real number. So what we are saying is that since this thing is always a multiple of 3, so whatever this calculation will be, I can always factor out 3 from the result, where a, whatever remains, it can be a fraction, it can be a whole number, it can be whatever. But we know the result is a multiple of 3. That means you can factor out 3 at any point in time. Now, that is an assumption we are making there. So we'll now go to step number 3. I'd like to step number 3. So step 3 now. Step 3. In step 3, we take n to be equal to k plus 1. We work from this. So in this case, we are just going to show that when I replace n by k plus 1, okay, then the answer will be a multiple of 3. Okay, so we'll take when n is k plus 1, that means 11 raised to power k plus 1 minus 8 raised to power k plus 1. Okay, I want to show that this result will always be a multiple of 3. So I simplify. I'm going to, this is equal to, by law of indices, I can write this as 11 in bracket 11 raised to power k minus 8 in bracket 8 raised to power what? K. Let us call this one star. Let's call this equation star. Okay, I'll come back to it later. Now, but from step 2, don't forget step 2 is an assumption. We have that 11 raised to power k minus 8 raised to power k is equal to 3a. It's an assumption. So we can make use of the assumption. So we'll find that we make 11 raised to power k the subject of the formula to get 11 raised to power k is equal to 3a plus 8k. Let me say that in proving PMI, you always use step 2 to conclude step 3. So we are going to use this step 2 to make our conclusion or simplify our result in step 3. So go back to star. Now substitute into star above, into the star above. So that now star becomes 11k plus 1 minus 8k plus 1 equal to 11 in bracket. Instead of 11k that was there before, I'll replace that 11k with 3a plus 8k. Then minus 8 in bracket 8k. Okay, let's simplify further. This is equal to I can open this bracket. If I open the bracket, I will get 3 in bracket 11a. So I just multiply 11 times this. That should be 33, but I don't want to write 33 because I have 7k. Obviously, you know you can't buy index number that 11. No, this is just, you know, not multiply it, except they have the same in. Then you can add their. But in this case, we just leave it as 11 in bracket 8 raised to power k. Then we then minus 8 raised to power k. Okay, so simplifying further, this is equal to 3 in bracket 11a plus 8k is common here. If I bring it out, I'm left with 8 to power k, 11 minus 8, which will give me 3 in bracket 11a plus 3 in bracket 8k. You can see clearly that 3 is common everywhere. I bring out the 3, I get 3 in bracket 11a plus 8k. So we are able to factor out 3 from this expression, which shows that this is a multiple of 3. Therefore, conclusion is that since we are able to show in step 3 that replacing n by k plus 1, then we will get a multiple of 3, then it shows that our statement Pn is true for all n, the set of natural numbers. And that is the proof for step 2. Now, in example 2, I take one last example. Let's take one last example. Example 3. Example 3. Now, in example 3, I'm going to prove that I'm going to prove summation I equal to 1 to n of I squared is equal to 1 over 6 n in bracket n plus 1 in bracket 2n plus 1. Okay? We are going to prove this one. Now, the proof. As usual, we start from the left-hand side. So, step 1. For n equal to 1, so what happened? Left-hand side is summation I equal to 1 of I squared, which is just 1 squared, which is 1. Okay, now let's take right-hand side. Right-hand side is 1 over 6. Now replace n by 1. In that formula, you get 1 plus 1 into 2 into 1 plus 1. Simplify this, you get 1 over 6. This is 2 in bracket, this is 3, which is obviously 1 over 6 times 6, which is 1. So left-hand side is equal to right-hand side. So Pn is true. That statement is true for n equal to 1. So it's true for n equal to 1. So step 2, we are going to assume that the statement is true for n equal to k. So that's our step 2. Step 2, so we'll say, suppose Pn, our statement is true for n equal to k. So I'm going to write the statement. We're going to write the statement, what it means to say it is true for n equal to k. That means summation I equal to 1 to k of I squared is equal to 1 over 6 k in bracket k plus 1, then 2k plus 1. Okay, that's what it means that the statement is true for n equal to k. Now, we go to step 3 straight away. And now step 3, we are going to be showing that the statement is true for n equal to k plus 1. So we take in step 3, we'll say let n be equal to k plus 1. As usual, we start from the left-hand side, okay, and we walk towards the right-hand side. We start from the left-hand side to the left-hand side. Now, starting from the left-hand side is summation I equal to 1 instead of kn, I go to k plus 1. I use k plus 1 of I squared. Now we're going to simplify this until we get a formula on the right hand side that looks like this one, but with n replaced by k plus 1, k plus 1, k plus 1. Okay, so now again, this statement, this means if I expand this summation for clarity, it means 1 squared plus 2 squared plus 3 squared plus and so on up to k plus 1 everything squared. But as summation is, we can sum to k first. So this can also be written as 1 squared plus 2 squared plus 3 squared plus up to plus k squared. Then before you add the k plus 1 squared, which we can write in compact form as summation I equal to 1 to k of I squared plus k plus 1 squared. And like before, these parts have been assumed to be true, so we'll just replace that from step 2. So that means I'll write there 1 over 6 k in bracket k plus 1 in bracket 2k plus 1 plus k plus 1 squared. This is by step 2. So using step 2 we can write this. Now what is left for us to simplify what we have here? Obviously, from here we have 1 over 6. K plus 1 is common here with these terms. So if we bring out k plus 1 there, we're going to have k plus 1 in bracket 1 over 6k in bracket 2k plus 1. Okay, then here we have plus k plus 1. Okay, now simplifying this further, we have k plus 1 in bracket. Now this is going to give me k in bracket 2k plus 1 plus 6 in bracket k plus 1 everything over 6. Okay, so if you further open that bracket, you're going to get which is equal to k plus 1 in bracket. For simplicity, you can bring the 6 under here, okay, because it's a product of two numbers. So this is going to give me 2k squared plus k plus 6k plus 6, which will be simplified to k plus 1 over 6 in bracket 2k squared plus 7k plus 6. Okay, this is a quadratic expression which can be factorized. So we arrive at a quadratic expression which we are going to factorize. Of course, we can take the factors. We can take the factors of that quadratic expression. So we can see clearly that this is equal to k plus 1 over 6 in bracket 2k squared plus 4k plus 3k plus 6, which is equal to k plus 1 over 6 in bracket. 2k is common here, so we have 2k in bracket, k plus 2, then plus 3 is common, and then we have k plus 2. So that the factors are, this is equal to k over 6 in bracket. This is now 2k plus 3, and then we have k plus 2. So rearranging that, we have finally we have this is equal to 1 over 6 k plus 1 in bracket k plus 2, and then in bracket 2k plus 3. Now this is true. Okay, let's convince ourselves that that is what we should arrive at. So if we go to the original statement, we're actually done with the proof. This is proof. But just to convince you that it's correct, the second side says that it's 1 over 6 n in bracket n plus 1 in bracket 2 n plus 2n plus 1. Okay, so if I replace, that was the right hand side in the original statement. Okay, so if I replace this by k plus 1, I'm going to get 1 over 6 k plus 1 plus 2 plus 1 plus 1. If I see like this is 1 in bracket, if you open that plus 3. So if we have replaced directly n equals to k plus 1, we are going to get polar, which we got by left hand side to the right hand side. So it's not just by substituting directly, it's by starting from the left hand side. You arrive at a formula that shows that when you replace k plus n by k plus 1, you are going to arrive at the same thing. And so that gives us the proof. The proof actually ends here, so this part is not actually not needed. So you don't have to show that. Once you have done that, you are finished with the proof. So conclusion, the conclusion here now is that Pn is true for all n, the set of natural numbers. Okay, before I round up the class, I'm going to give you some assignment which you are going to do on your own. Okay, I'm going to give you some work you are going to do on your own. So I call them assignments. Number 1, prove that summation I equals to 1 to n of I cube is equal to 1 over 4 n squared in bracket n plus 1 squared, n plus 1 all squared. That's number 1. And number 2 says prove that 7 raised to the power 2n minus 9 is a multiple of 2 for all n, the set of natural numbers. This is for n, the set of natural numbers. Okay, so with that, we come to the end of the class for today. Thank you very much.